I don't think I've ever been live streamed before, so this is exciting.
Yeah.
Okay, we can start now, yeah? Okay, good afternoon, everyone. Good morning and good evening to all of you in different time zones. Welcome to the 10th edition of the Combinatorics Today's series. We are very happy to see you again. And we are very grateful to the Dean of the Faculty of Mathematics and Natural Sciences ITB, Professor Wahyu Sri Kutomo, for giving us a constant support to this event. So we can have this in 10 editions for this year. We also welcome to all colleagues and students for attending this program. Thank you so much for your participation in this program, and we are really appreciated. And I warm welcome to our speaker for today, Professor Catherine Greenhill. She is the professor at the University of New South Wales, Australia, and she's also a chair of the Women in Mathematics Special Interest Group of the Australian Mathematical Society. And she's an editor-in-chief of a famous journal, which is the Electronic Journal of Combinatorics, and she received many medals for her achievements. And we are very lucky and grateful to have Professor Catherine Greenhill as our speaker today. In her busy time, she's still willing to receive our invitation to speak on this event. Hi, Catherine. How are you today?
Very well, thank you. How are you, Eddie?
I'm fine. So are you in Sydney now?
Yes, Sydney, yes. A rainy Sydney today.
Okay, so what time is it in Sydney?
It's just 6:04 in the evening.
Oh, okay, yeah. Great.
Not late.
Not late, yeah? Okay, so thank you again for being with us today. And I should mention that this program is organized by the Combinatorial Mathematics Research Group, the Faculty of Mathematics and Natural Sciences, Institut Teknologi, Bandung. And now we are all very excited and honored to have Professor Catherine Greenhill from the University of New South Wales, Australia. She will deliver a lecture with the title Results about Random Hypergraph Proof using Asymptotic Enumeration Formulae, and will be chaired by Dr. Hilda Asyaton. And before I give the control to Dr. Hilda, I would like to invite our chair of our Combinatoric Mathematics Research Group, Dr. Joko Suprianto, to give a welcoming speech. Pak Joko, time is yours.
Yeah, okay. Thank you, Pak Edi. Hello, good afternoon, everybody. Welcome back to our Combinatorics seminar, Combinatorics Today series. First of all, our sincere gratitude to Professor Catherine Greenhill of the University of New South Wales, Australia, for taking the time to give this lecture. Professor Greenhill, you are, as we have known, a 10th speaker. That is the last speaker in our seminar series for this year. And the topic of your talk is quite interesting to many combinatorialists here, I'm sure. Although so far, there is only, in particular, in our research group, there is only one member who has been doing some random graph. That's Hilda. I'm also sure that you have known about it. But accidentally, in today's seminars, there is also our colleague from Japan, Professor Nobuaki Obata. We have been doing some collaborations since several years ago. And he's also expert in graph theory and some aspects in probabilistic theory, and also its connection with some aspect in quantum graph or quantum theory, something like that. So I am very sure that we will have an active discussion after your talk. And we are also very sure that your talk will broaden our knowledge in combinatorics and in particular in the graph theory. So once again, Professor Greenhill, thank you very much. And to all the participants, enjoy the seminar. Thank you.
Thank you, Pak Joko. And now, before I ask Dr. Hilda to share this talk, let us together have a group photo, because I think this photo will be going to be important photo later on. Yeah. And now, Pak Yusuf, can you help us?
Yes, okay. Everyone, please open your camera. Okay, so there is 27 participants.
Mm-hmm.
We could do this in one page. So I'm gonna take a screenshot of this meeting. Okay, 1, 2, 3, smile. Okay, thank you, everyone.
Okay, so now I ask Hilda to share this session. Okay.
Okay, thank you, Pak Edi. Good afternoon and good evening, everyone. It is nice to meet you again in the Combinatorics Today series. It is a great pleasure for me to be the chair for our speaker, Professor Catherine Greenhill from the School of Mathematics and Statistics, University of New South Wales, Australia. Before we proceed, let me share with you the summary of Professor Greenhill's curriculum vitae. Okay, it's a nice picture of Catherine. Catherine Greenhill obtained her bachelor and master degrees from University of Queensland, Australia, and her PhD from University of Oxford, United Kingdom. After finishing her PhD, she had 2 postdoc positions. The first one was in University of Leeds, UK, and the second one was in the University of Melbourne, Australia, where she worked with Nick Wormald, who was my supervisor at the time. I was doing my PhD. So that was the first time I met Catherine. She joined the School of Mathematics and Statistics, University of New South Wales in 2003 and was promoted to a professor in January 2019. Currently, Catherine is serving as the chair of the Women in Mathematics Special Interest Group of the Australian Mathematical Society. And she was also one of editors-in-chief of the Electronic Journal of Combinatorics since 2015, and also a member of the Faculty of Science Promotion Committee for Promotion to Professor, UNSW. I should also mention here that Catherine was the president of Combinatorial Mathematics Society of Australasia in 2011-2013. Catherine has published 76 papers in journals and conference proceedings and has been awarded many research grants from Australian Research Councils and UNSW. Due to her excellence in research, she has been awarded the 2015 Christopher Haid Medal in Pure Mathematics by the Australian Academy of Science and the 2010 Hall Medals by the Institute of Combinatorics and its application. And now for the research interest, I decided to just quote what Catherine has written in her website. So her research looks at fundamental combinatorial objects such as graphs and hypergraphs and aim to very basic question that can be very difficult to answer. Solution involve methods from combinatorics, probability, theoretical computer science, and occasionally from statistical physics. She has studied the structure of random graphs and hypergraphs, obtained asymptotic enumeration formula for various combinatorial objects, and analyze the performance of Markov chain algorithms. She pointed out that in many areas, complex discrete system can be modeled using graphs and hypergraphs. And her research provides tools such as algorithms and formula to get better understandings about these complex discrete systems. Now to end this summary, I would like to show you the visualization of titles of her papers. And today we will have opportunity to learn more about her current research. Okay, now without further delay, I invite Professor Catherine Greenhill. Catherine, the stage is yours. You have 60 minutes.
Well, thank you very much, Hilda, for your introduction. I'll just see if I'm sharing my screen now. Can you see that?
Yes.
Excellent. And thank you, Eddie, for the invitation, and Joko also for your kind words at the start of my talk. I'm really happy to be here talking to you today. And I'm going to be talking about the three areas of my research interests that Hilda mentioned are going to come up in this talk. The common theme that I decided to talk about is results that you can prove using asymptotic enumeration formulae, but there'll be 3 different results with 3 different flavors. So if you don't enjoy one part of the talk, just wait a little bit longer and you'll get a different flavor coming along. And let me see if I can progress my slides. Yes, I can. It's joint work with a bunch of people. So I'll mention these names again when we get there. Firstly, let's discuss what I mean when I say asymptotic enumeration. So we have a sequence of combinatorial sets, omega n, and they're indexed by n. You want n to tend to infinity. That's the asymptotic part. And you can think of omega n being the set of 3 regular graphs on n vertices, let's say. In this example, you see that n has to be even. So there may be constraints like this on n, as long as you can send n to infinity along that subset of the positive integers. We want to know how many elements are in omega n. Usually omega n is an exponential size in n, or possibly even bigger. And usually there's no closed formula for omega n, for the size of omega n. So we want to find an approximate formula, which should get closer and closer to the real answer as n gets larger. So the relative error should tend to 0. And just as a warm-up, we can think of omega n as the set of all permutations on n objects. And we know there are n factorial of those permutations, okay? So we can write this down in a very simple way, but if you didn't know the notation n factorial, or if you wanted to know how these sets grow as n tends to infinity, then you might apply Stirling's formula to get this approximation, which can be easier to work with in some settings. So Stirling's formula says n factorial is equal to this approximation times 1 plus an error, and the error is, you know, at most some constant times 1 on n. So that's the big O notation. If you really don't mind how big that error is, as long as it's tending to 0, then you might just write this relative error here as little o1, which just means some expression, a function of n that tends to 0. Okay. I'll mainly be talking about enumeration of graphs and hypergraphs with given degree sequences. So the degree sequence I'll use, I'm going to use the letter K in boldface to denote this sequence, K1 up to Kn. And we want degree J to have, vertex J to have degree Kj for all of the vertices. And my vertex set is always going to be just, I'll label the vertices 1 up to n, with n square brackets being shorthand for this notation. I don't assume that my degrees are sorted in any sort of non-increasing order. The degrees can be in any order. And then I write G of K for the set of all graphs with the given degree sequence. And I'm always going to assume that K is graphical, so that this is a non-empty set. Okay. And a special case is regular graphs, when all of the degrees have to have the same, all of the vertices have to have the same degree, and we'll use K with no boldface for that degree. and write G of nk for this set. So n vertices all with degree k. Okay. The first thing people tried involved the configuration model to try to enumerate these sets with a given degree. The configuration model, often attributed to Bolabash, but it arose in about sort of 3 different places at the same time, is also a way to generate graphs with given degrees and to calculate probabilities for random graphs with given degrees. So here is an introduction to the configuration model. If you want n vertices, then you should start with n cells. Each of these little circles, ovals, is a cell, and the jth cell contains kj points. So this cell has 1 point. That means this corresponding vertex will have degree 1. And we let capital M be the sum of all the kj. In this case, it's the number of points. So each of these little blue dots is a point, and we can tell all the points apart. Now, to take a configuration, you randomly partition the capital M points into pairs. So you're going to get M over 2 pairs, and I've shown them as a little line here. Then you just shrink each cell down to a vertex, and now you have a multigraph with the given degree sequence. We say multigraph because sometimes you might get a pair that joins 2 points from the same cell, and that will give you a loop over here. Or we might have 2 different pairs between the same 2 cells, and that would give us a repeated edge. In this example, we've got a simple graph, but we might get a multigraph. Okay, so that's the configuration model. And it's useful partly because you can just throw those pairs in very easily. Also, every simple graph with a given degree sequence arises from exactly the same number of configurations. So all of the pairs that are going into a particular cell, they can be assigned to points in any way, where you get these kj factorials independently at each vertex. And this only depends on the degree sequence, not on the graph G. We can also write down easily how many configurations there are. That's just the number of ways to pair up capital M things. And so we can write down the number of graphs with a given degree sequence using these quantities, so long as we know, and well, we can write it in terms of the probability that a randomly chosen configuration with the given degrees produces a simple graph. And in this talk, if I say randomly chosen, I mean uniformly at random, where every element has the same probability. Okay, so what's going on here? This is the number of configurations. And if you multiply by the probability of obtaining a simple configuration, then these 2 factors together give you the number of simple configurations with the given degree sequence. And each graph over here is represented by exactly this many of those configurations. So we have to divide by this product in order to make sure that we're not counting each graph multiple times. And that is how we write the number of graphs with given degree sequence in terms of the probability that a random configuration is simple. So if we want to estimate this number, we should just estimate this probability. Okay. So how do we do this? Well, a graph is simple. A multigraph that arises from the configuration model is simple if and only if it has no 1 cycles, which are the loops, and no 2 cycles. And we can analyze this number. So xj could be the number of cycles of length j in a randomly chosen configuration or a randomly chosen multigraph. Let's stick with configuration here. When the maximum degree, let's say, is not very large, so when you're in the sparse case, then the degrees are asymptotically independent Poisson random variables. They're sort of counting rare events. And that makes them quite nice to work with. And in particular, if you have a Poisson random variable with a mean of lambda, then the probability that that random variable is 0 is just e to the minus lambda. So you calculate the expected number of 1 cycles, the expected number of 2 cycles, and then the probability that the random configuration is simple is just e to the minus lambda 1 minus lambda 2, where lambda 1 and lambda 2 are those corresponding means. Okay. using this approach, Bender and Canfield back in 1978 looked at the regular case where the degrees are all constant k. So k does not grow with n. It's like k equals 5 or k equals 100 or something. And they got an asymptotic estimate for the probability that the random configuration is simple, and it looks like this. You can see if you want this probability, oh no, I won't say that. So it tends to e to the minus k squared minus 1 over 4. And then Baylor-Bolobash in 1980 was able to extend this analysis to irregular degrees and also allow the maximum degree to grow, but only up to root log n. And he got this slightly more complicated expression involving this parameter. So I am, in this talk, I'm going to be hiding some of these messy details away. We won't go through all of the details of all the results. In terms of calculating the probability of simple, Svante Jansen was able to push the sparse case up a little bit, get a slightly different expression here. And then McKay and Warmold in 1991 gave, oh, well, that's earlier, but they gave a very precise formula with lots of significant terms, but it's only when the maximum degree is little o of m to the 1/3. So this is essentially the number of edges. It's twice the number of edges, and the maximum degree has to grow slower than m to the 1/3. Okay. Using these sort of results about the probability of being simple, you can come up with asymptotic formula for the number of graphs with a given degree in the sparse case. For example, the one arising from Bolobash's work and the formula that arises from McKay and Warmold's work, both using the configuration model, and the McKay-Warmold one had another layer of argument on top of that, which is called the switching method. Then at around the same time, published slightly earlier, McKay and Mormont also analysed, were able to obtain an asymptotic enumeration formula at the opposite extreme when all of the degrees are quite large, basically around linear, n over log n up to n on 2, and the degrees shouldn't vary very much. So they're fairly concentrated around their mean. And this is using a completely different argument where you have to do multi-dimensional complex integration to extract the coefficient of a generating function. So it's an interesting approach. The calculations are a little bit scary, in my opinion, although I have worked in this dense case as well. But for a long time, we knew how to handle sparse things with combinatorial arguments, and we knew how to handle dense things as well. But then a bit more progress, Svante Jansen using the result I showed you earlier, I guess, and probabilistic arguments extended the sparse range a little bit. Barvanok and Hartigan gave an alternative approach to the dense range. Jane Gow and Nick Warmold were able, for the first time, to enumerate some sort of realistic heavy-tailed degree sequences, the sort of networks that arise in real-world applications, where a lot of the vertices have a low degree, but some of them have a very high degree, which couldn't be handled by any of our existing methods. But then the really big breakthrough was Anita Libernau and Nick Warmold, who came up with a new recursive approach, and they obtained an asymptotic enumeration formula under this condition. And little k here is always going to be the average degree, which equals all of the degrees if it's regular. I will say a little bit more about this approach soon. So far, this was just a survey about some of the enumeration results for graphs with given degrees. And I don't really want to talk about that. I want to say, what can we do with these formulae? So here are 3 things we can do. We can come up with a model for the degree sequence of a uniformly chosen random graph or hypergraph with m edges. So you specify the edges, choose one randomly, and say, what does the degree sequence look like? You can use these formulae to help you calculate probabilities and expected values for random graphs or hypergraphs. And you can analyze algorithms or processes that run on graphs or hypergraphs. So I'm going to try to tell you a little bit about an application that falls into each of these 3 categories. just to give you the flavor of how it works. Okay. So the first application is to the degree sequence of a random graph. Yeah, so first we'll talk about graphs and then hypergraphs. Now, if you think about the sort of binomial random graph model, I don't know if you've heard of that one, you take all the possible n vertices and you just flip a coin to decide whether between any two edges, between any two vertices, there should be an edge. And if your coin has probability P of coming up heads, then you put an edge with probability P. And you do that independently for all possible edges. And if you do that, the degree of a given vertex has a binomial distribution with these parameters, binomial n minus 1p. And so we want to compare the degree sequence of a randomly chosen graph with m edges to this thing. So far, it's a sequence, x1 up to xn, of independent binomial random variables, and each one of them has this distribution. But then we need the sum of the degrees to add up to 2m. So you take this sequence of independent binomials and you condition on the sum being equal to 2m, all right? And that gives you, this conditional space is the thing we want to compare the degree sequence probabilities. Now you can check that for any degree sequence which adds up to 2m, the probability that you see this particular degree sequence or sequence in this conditional binomial space is exactly this product of binomials divided by this quantity. It's funny because the probability P doesn't show up at all. It's just because all the P's and one minus P's all cancel. So we want to compare the probability of seeing a particular degree sequence with this quantity. Now, McKay and Mormont in 1990 conjectured that the probability that a randomly chosen graph with n vertices and m edges should have degree sequence k is asymptotically equal to this expression that we just looked at before with all the binomials, but not exactly. You have to adjust it slightly, and the correction factor adjusts for the fact that these choices are not really independent. And the asterisk is a little warning that there are some mild technical assumptions that I'm not going to tell you. Okay, so Nick and Brendan made this conjecture because they knew a formula for the sparse case and they knew a formula for the dense case. And in those two extremes, they saw this behavior. So they thought surely the behavior must hold everywhere. And they could prove it at the two extremes of the sparse and the dense. And then when Anita and Nick had their breakthrough result, they actually proved the conjecture in full, and they used, that was their main result, the degree sequence result, and their enumeration result followed from the degree sequence result. Whereas with the earlier work, first people did the asymptotic enumeration, and then as an application, they got the distribution of the degrees. So I'll tell you a little bit about what they showed. Again, under some mild assumptions on the degrees that I'm not going to tell you. They showed the probability that a randomly chosen graph on n vertices with m edges, the probability this random graph has a given degree sequence k is equal to what it equals in the binomial sequence of binomial vectors that I showed you before, the thing with all the binomial coefficients. And here is the correction factor. So it's basically e to the quarter minus this stuff plus a vanishing relative error. And what is all this stuff? So firstly, k is the average degree. Lambda, which is k over n minus 1, is the edge density, the proportion of all possible edges that could be present, which actually are present. And gamma 2 is this quantity. So we can think of lambda as basically a constant in the dense-ish case, or, you know, it's not always, I shouldn't say that, but lambda is just lambda. Gamma 2 looks like this. And I think the mild assumptions imply that each of these squares is order n. So the sum overall is order n squared, and gamma 2 is overall at most a constant. So this is the degree sequence result that they proved. What does the degree sequence of a randomly chosen graph with m edges look like? Well, it almost looks like this binomial thing with this correction factor. Okay. And from that, you can get an enumeration result just by multiplying by the number of graphs there are with m vertices, m edges, which looks like this. And then when you remember what the probability of a given degree sequence is in the binomial model, you get this expression. So that's the enumeration result in full. And finally, with all of these binomials, you can rewrite them as factorials, and then you can apply Stirling's approximation that we saw at the start of the talk and write the whole thing like this with the edge density playing a large role. Actually, you leave these ones alone, don't you? You just apply Stirling to these two. And so which of these two formulas you prefer will depend on what you want to do with it. Okay. So that followed from the Libernau and Mormont result for graphs. They used their method to also look at the degree distribution for bipartite graphs and directed graphs with a given number of edges. And the dense case for those two had already been covered by Brendan McKay and his honours student at the time, Fiona Skirman. And now I ask, what about hypergraphs? So we'll focus on R uniform hypergraphs where every edge has size R. So this generalizes a two uniform hypergraph, which is simply a graph. This is a cycle in a three uniform hypergraph. And it's what we call a loose cycle because the edges only overlap in one vertex and then you move on to the next one. And if all of the vertices in the graph are here, then this is a loose Hamilton cycle. Okay. In hypergraphs, what is a simple hypergraph? Well, a simple hypergraph is one where you have no loops and no repeated edges. And a loop is just an edge that has a vertex repeated in it. So that's how you generalize the idea of a loop for a multigraph to a hypergraph. And we want to focus on simple hypergraphs. So let HR of K be the set of all simple R uniform hypergraphs on the vertices 1 up to n with a given degree sequence. I'm using G for graphs and H for hypergraphs. And again, if it happens to be regular, I'll just write HRNK for this. Okay. Cool. So I'll tell you a little bit about the asymptotic formulae that are known for hypergraphs because those will be some of the tools that we use in the rest of the talk. Dudek, Fries, Ruczynski, I should say in Bolabash's enumeration paper for graphs, he did mention a formula for hypergraphs. Again, when the maximum degree, I think this time it's the order of log n. But going further than that, the first paper was Dudek, Fries, Ruczynski, and Solaikis in the regular case when k is little o root n, which is still pretty sparse. With Blanovsky, we generalize this to irregular degrees. The size of the edges can also grow slowly as long as this formula holds. And these were both combinatorial arguments with switching. Using a different method, Kuperberg, Lovett, and Pelled gave a formula in the regular case where the number of edges is at least n to the c, and actually also for the complement. So this is a regular dense result. And then using the method developed by Libernau and Wormold, together with Nina Kamchev, these guys applied their results to hypergraphs, R uniform hypergraphs. And they showed that the degree sequence of a random R uniform hypergraph with M edges can be written using a kind of sequence of independent binomials conditioned on having the correct sum in the way that we did before, times a correction factor. So a generalization of the result they had before. And these are the probabilities in the hypergraph version of the binomial model for the degrees. But the problem is that the correction factor they got actually gets bigger and bigger with R. It's exponential. It's got an e to the R minus 1 on 2 in it or something like this. So that's not ideal. And they actually conjectured in their paper that a better model, rather than using the binomial random variables to build up your sequence, they said we could use independent hypergeometric random variables instead, conditioned on having the correct sum, which for an R uniform hypergraph, the sum of the degrees is R times M rather than 2 times M. So this is like a generalized handshaking result. Now, what is going on with these parameters? The hypergeometric random variable says you have, you need to choose M objects, which for us are the edges, out of a possible N choose R objects. And you have a success if your edge contains a specified vertex, because we want to model for the vertex degree. And so how many successes are there? Exactly N minus 1, choose R minus 1. So you just make your choice and count how many successes you have. You put an independent hypergeometric in each of x1 up to xn and condition on them having the right sum. Okay, so then this is my first result that I wanted to talk to you about together with Mikhail Isaev, Tamas Mackay, and Brendan McKay. We gave an asymptotic enumeration formula for hypergraphs with given degrees in the dense case. We have an implicit formula where you have to be able to come up with a solution to some equations and solve the determinant. But if you have this additional condition that the degrees don't vary from the average very much, then we have an explicit formula, which we've just written down. And using that formula, we could verify the conjecture of Kamchev et al., which says that the hypergeometric distribution is a better model for the degrees, and that is a smiley face. So this is the same information about the hypergeometric distribution. I've just given it a name. So TRNM is the random vector of n independent copies of this distribution conditioned on having the correct sum. And what we proved for our range of parameters, which is don't try to absorb all of this stuff. It's a bit of a mess, but if our conditions hold, then the upshot is that the probability that the random hypergraph with M edges has the given degree sequences is basically 1 plus little o1. All of this stuff is vanishing. So the probability in the sequence of hypergeometrics is actually giving you the right probability, except for some strange degree sequences, which are very, very rare. This first condition says that the density is high enough, lambda is high enough, and similarly not too close to 1. And this is just a parameter that we found it convenient to express our answers in. So the main takeaway is there's no correction factor here. The correction factor is 1 plus the little o1. Okay. So if you care about degree sequences and you want to do some calculations with them, you can work with these hypergeometric random variables instead. Okay. The second application I wanted to tell you about is calculating probabilities and expectations. So we're going to work with graphs first. You think of a set of possible edges, which are forbidden edges, and they go into a subset called X. And then G of Kx is all graphs with degree sequence K, which avoid all the edges in X. So they don't have any of your forbidden edges in them. And this can be a useful thing to know. And the fact is, if you want to find the number of graphs that contain a particular set of edges, then it can be useful to know how to count the number of graphs that avoid those edges because of the connection I'll describe. Here, little x is the degree sequence of the forbidden edges. And we want, let's say the edges we want to include are these red edges. This is actually our set of 2 edges, x, and the numbers in brackets are the degrees. So what you can do if you insist those 2 edges are present in the graph, you may as well actually remove them and decrease the degrees of everything and then fit all the other edges in while avoiding those dashed edges so that you don't end up with them twice using the diminished degree sequence, such as this cycle. And then after you've chosen this cycle, you can stick all the edges of X back in, and now you've got a graph that contains X. So the point is to construct graphs that contain a set of edges, you can instead work with avoiding a set of edges by reducing the degrees. And there's, here I've got at least 2 ways of doing this. So each choice which avoids X gives me a choice that includes X. For example, I can use this formula, if I had one, to calculate the expected number of perfect matchings in a graph with degree sequence k, simply by noting that if I specify a perfect matching, every vertex should have degree 1 in the perfect matching, and I can subtract 1 from all of the degrees and count the number of graphs that have this lower degree sequence that avoid x, and that equals the number of graphs with the actual degree sequence that contain x. So this number divided by the total number of graphs in G of k gives me the probability of containing a specific perfect matching. And by linearity of expectation, because of all the symmetry, all I have to do is multiply by the number of choices for the perfect matching on n vertices, which is this, and now I've got the expected number of perfect matchings. This is hopefully meant to convince you why it might be useful to be able to count graphs that avoid a certain set of edges. So Brendan has been leading the way on this. He had a formula in the sparse case and also a formula in the dense case, allowing the number of forbidden edges to be roughly linear as well. Okay, for graphs. But you can do all of the same stuff for hypergraphs. So in the same way, let HR of kx be the set of hypergraphs with a given degree sequence. They always are uniform and they avoid all the edges of x. So my PhD student, Haya Al-Dasari, worked on this problem. And this is the result she came up with. So we were working in the sparse case using combinatorial methods. And her formula works if the number of edges times the cube of the maximum degree is little o of m squared, and a similar requirement over here. And this requirement is just so that we know how to enumerate hypergraphs. Okay. And in that paper, that 2019 paper, we calculated the expected number of perfect matchings, and we calculated the expected number of loose Hamilton cycles in a random k-regular R-uniform hypergraph, just to illustrate the usefulness of the method. Haya also wrote another paper calculating the expected number of spanning trees in sparse graphs with a given degree sequence. It didn't have to be regular. So those are just a couple of applications, extending some work that I'd done previously for graphs. But the application that I really want to tell you about where we're using this formula involves something called the small subgraph conditioning method. And I don't have time to really tell you too much about what this is about, but Robinson and Mormont introduced this method to analyze the number of Hamilton cycles in a random graph. And it can be used to prove that in a random object, some nice subgraphs or substructures are present. So the number of random graphs is positive, let's say, with probability which tends to 1. And sometimes this method works when a simpler method, the second moment method, fails. Robinson and Mormont, as I said, introduced this method to show that almost every k-regular graph contains a Hamilton cycle when k is at least 3. And how it works, you would take y to be the random variable, which is the number of Hamilton cycles in a uniformly random k-regular graph. And you would have to also look at the number of cycles of length j in a uniformly random k-regular graph. And you have to calculate the expected value of y, so the expected number of Hamilton cycles, the second moment of y, and also the expected value of the product of y and xj, which is the expected number of ways you can choose some Hamilton cycle and some j cycle in your random graph. And there are some conditions that you have to show that they satisfy. Okay. So using this nice method, a sequence of results were proved. We know quite a lot about the structure of random regular graphs from this method. And in particular, Hanya Robolewska in 1992 proved that almost every k-regular graph contains a 2-factor if k is at least 3. And a 2-factor is a spanning 2 regular subgraph. just as a perfect matching is a spanning one regular subgraph, which is also called a one factor. So we already knew about one factors, and Hanya showed almost every k-regular graph contains a two factor by applying the small subgraph conditioning method. And up until that point, most people used the configuration model for their calculations when they were applying this method. But instead, Robolewska used asymptotic enumeration formulae to perform her calculations. So let's now talk about hypergraphs. There's only a few applications of small subgraph conditioning method to k-regular R uniform hypergraphs. And here K and R are constants. And until quite recently, there was basically only one of these structural applications of the small subgraph conditioning method. So Cooper, Fries, Malloy and Reed looked at perfect matchings in 1996. And then a former undergraduate student of mine, Mikhail Isaev, who was my postdoc at the time, and Reshma Ramadurai, who was also my postdoc, we analysed loose Hamilton cycles in these random hypergraphs. And a former honours student, Gary Liang, Mikhail Isaev again, analysed spanning trees using the small subgraph conditioning method. And the one I'm working up to is some work by my current honours student from this year. Now, those results on the previous slide were also done by working in the configuration model for hypergraphs. But if you do that, there's actually a problem when you try to take what you've learned about the configuration model and pull those results over to the hypergraph world. In graphs, you can do it quite easily because the event that the graph is simple is exactly saying no one cycles and no two cycles. And conditioning away cycles is very easy in this method. But for hypergraphs, you have a problem because the event of being simple says no one cycles and no repeated edges, but you can't rule out all two cycles, and you also can't forget to rule out the repeated edges. So you can't just condition away cycles to get simplicity. And as a result, you can't transfer expected value of y from the configuration model to the random hypergraphs, which is a problem. So you've done all this work in the configuration model, and the only way we knew to get around it was we still had to apply a hypergraph enumeration result at the very end just to tidy up this problem. So that's sort of annoying. And one good thing that came out of my the work of my honours student this year, he wanted to extend Robolewska's result about two factors from graphs to hypergraphs. And he also followed her lead and used asymptotic enumeration formulae rather than working in the configuration model. And as a benefit of this, we just didn't have to worry about this complicated extra step from before. And this is what he's proved, which we will be writing up into a paper soon. So what you get with hypergraphs is you get a threshold result. So K and R are fixed integers at least 3. Then there's some unique threshold, a degree threshold, which is a function of R, the function of the edge size, so that whether or not you have a two factor in your random hypergraph depends on whether your degree is above the threshold or below the threshold. If your degree is above the threshold, then you have a hypergraph with probability, your hypergraph contains a two factor with probability tending to 1. And below the threshold, this probability tends to 0. And this is what the small subgraph conditioning method tells us for the two factors. It's sort of interesting because you really have to have quite a high degree for a given edge size in order to have these two factors. The threshold is actually exponential in R. And the same thing happens for the perfect matchings and for the loose Hamilton cycles and the spanning trees. There are these different thresholds for the degrees that you have to be above in order to have these structures show up. Okay. And just as a bit of a flavor of how the proof works, the random variable that we analyze using the small subgraph conditioning method is the number of two factors in a randomly chosen hypergraph. And I'll tell you how we calculate the second moment, which is the most complicated part of the argument. So we're going to need, for the second moment, we have to have two factors. We're counting all the possible ways you could have two factors within your hypergraph, and we multiply by the probability that we see that hypergraph. So each two factor is a two regular subgraph, and we can think about what the intersections can look like. And every vertex in the intersection has degree 0, 1, or 2. And it turns out those are the only parameters you need to know: how many vertices have degree 1 and how many have degree 2. Then you can sum over all the ways to choose your intersection. That's combinatorial bit there. Once you have an intersection, you want to choose a two regular spanning subgraph that contains your intersection. You do that using an asymptotic enumeration formula. To choose your second two factor, you have to contain all of the intersection and avoid everything else in the first two factor that you just chose. Avoid all the edges of F1 that aren't in the intersection, because otherwise your intersection would be bigger than I. We want the intersection to just be I. So you have to sum over all the ways to choose F2, and I can calculate that using an asymptotic enumeration formula. Now we have two factors that overlap in a set of edges called I, and we sum over all the number of ways to complete F1 union F2 to an K regular hypergraph. And I can calculate this number using an asymptotic enumeration formula. And finally, you multiply by the probability that this hypergraph H that I've just constructed is the random hypergraph that I chose. And that probability is uniform. So you need to know the number of hypergraphs, which we have an asymptotic enumeration formula for. So once you put all that together, these last 4 steps out of 5 are just writing down the asymptotic enumeration formula and then dealing with the expression that results. Okay. And I want to say just a little bit about this third application, which is algorithms for generating graphs or hypergraphs. Well, algorithms for generating hypergraphs randomly. So how can we efficiently generate or sample a random hypergraph from this set of all hypergraphs which are uniform with the given degree sequence? Well, there is a configuration model for hypergraphs. So you could choose a random configuration in an analogous way that I described with graphs, shrink the cells down to vertices and see whether we have any loops or repeated edges. But the loops will become too common if R times the maximum degree is much bigger than log n. So it's only efficient if this bound holds, and that doesn't allow the degrees to grow very fast. Not only that, but Days 11, Meesom and On proved a couple of years ago that even deciding for a given degree sequence whether or not a hypergraph exists with that degree sequence, even a 3 uniform hypergraph exists, is NP hard. This is really surprising. So in the graph case, you can just apply the Erdős-Gallai conditions and decide that question in polynomial time. In the hypergraph case, even for 3 uniform hypergraphs, it's NP hard. And so that suggests that generating these hypergraphs randomly is also hard. But like every hard problem, that doesn't mean you can't do it. It just means there will be some instances where it's going to be hard, but for a lot of them, it should be possible. And this was work that I did with Martin Dyer, Peter Clear, James Ross, who's my master's student, and Lane Stauchi. And our idea is to use bipartite graphs because we know how to sample bipartite graphs with given degrees. So here's the connection. Here's a hypergraph. Okay, this is a 3 uniform hypergraph with 6 vertices shown with the blue dots. And I've got 4 edges that I hope you can see. So one is 1, 2, 3, one is 1, 2, 4, one is 2, 5, 6, and one is 4, 5, 6. From the hypergraph, I can make the incidence matrix with the 6 vertices on the rows and the 4 edges on the columns. And now you treat that incidence matrix as a biadjacency matrix, and it will give you this bipartite graph. The vertices on the left, which are blue, correspond to the vertices of the original hypergraph, and the vertices on the right correspond to the edges. And so each vertex on the right has degree 3 because I'm in a 3 uniform hypergraph. And just to make that a little bit clearer, here's the first edge. It contains vertices 1, 2, 3, and it corresponds to these edges here. Okay. So this is a really nice connection. And every simple hypergraph with m edges, you can code it up into a bipartite graph in m factorial different ways. You have to label the m edges. That's the only thing you have to do. Conversely, if you have a bipartite graph over here and it has degree sequence k on the left and it has every vertex having degree r on the right, you can ask, does this bipartite graph correspond to a hypergraph with the given degree sequence? But the problem is 2 of these vertices on the right might have the same neighborhood, and that would correspond to a repeated edge, which we're not allowed to have. So the bipartite graph gives you a simple hypergraph if and only if no 2 vertices on the right have the same neighborhood. Okay, so the reason why we wanted to use this connection is that, as I said, there are a lot of algorithms known for generating bipartite graphs with given degrees. And I'm not going to say much about these, but a good one, if this bound holds for the sparse case, is an algorithm by Amon, Gao, and Wormold, because it gives you exactly uniform output, exactly uniform, as the configuration model also does, but this one goes for much larger degrees. Then there was a paper by Jerem, Sinclair, and Vagoda, which was a really impressive piece of work about approximating the permanent, which is counting perfect matchings, approximating perfect matchings in any bipartite graph. And using this, you can actually generate graphs with a given degree sequence. Bezakova, Batnagar, and Vagoda showed a slightly better way with a better running time. But basically, for any degree, you can approximately uniformly generate in polynomial time using simulated annealing. And a simpler algorithm is to just take 2 edges randomly and rewire them and do that lots of different times in different places. And that's called the switch Markov chain. And there are several results about that, including some of mine. Okay, this is the algorithm we came up with to use sampling for bipartite graphs to help us sample hypergraphs. So we called it Hypergraph Sampling. It takes the degree sequence and the edge size, and A is an algorithm for generating bipartite graphs. And we just treat this as a black box. We don't need to even know how it works, really. It has to sample bipartite graphs with degrees K on the left and RRR on the right. And all you do is you keep choosing a random bipartite graph, which we'll call B, using this algorithm A, until it's going to give you a simple hypergraph. So all the vertices on the right have to have distinct neighborhoods, and then the corresponding hypergraph is simple and you output it. So if you prefer these sort of process diagrams, you just keep choosing a bipartite graph from this algorithm A. You ask yourself, is the output, the corresponding hypergraph, simple? If it is, that's the output, and otherwise you go round the loop again. And the question is, how many times do you go around this loop? So when you analyze the runtime, what you get is basically, well, for each time you go through the algorithm A, you've got the runtime of performing that algorithm, and the expected runtime of our algorithm is the expected number of times we expect to go through that loop times the runtime or the expected runtime of A. So what we need to know is, how many times do we expect to have to run this algorithm? And that's just a geometric random variable with the expected number of times you have to do it is 1 over the probability of success. And the probability of success is exactly the number of bipartite graphs where no 2 vertices on the right have the same neighborhood, divided by the total number of bipartite graphs with those degree sequences. Okay. And so with Martin Dyer and those other 4 authors, we showed that if this condition holds, that R squared K max squared is little o m, then we had this lower bound on the probability of a success. And I'm not going to really explain what's going on there, but we then gave some special cases which said maybe the probability of success is at least 1/3 or something, and then you would expect at most 3 trials. And in order to prove this, we used an asymptotic enumeration formula for bipartite graphs, which was my first sparse asymptotic enumeration work with Brendan and Jimmy Wang back in 2006, and a switching argument on top of that. So this is just to indicate that analyzing algorithms on graphs, sometimes these asymptotic enumeration formulae can help. Okay, and one last application I wanted to mention, which is not one of my own, but involves Matthew Kwan, who was an honours student at UNSW and has gone on to great things. So Ferber, Kwan, Narayanan, Saw and Sawney recently studied something called friendly bisections of random graphs. I think this means you split the vertices of the random graph into two halves, which are almost exactly the same size. Maybe they just differ by one. And then you have to sorry, I was just looking at the chat. Then you want to make sure that each vertex on one side has lots of edges going across to the other side. And I think they proved that these things exist, confirming a conjecture of Ferretti, and their proof made really heavy use of our asymptotic enumeration formulae, which they said were powerful, which was nice. Nice to see an application there, studying a particular process. And I think that's all I've got. So thank you very much.
Thank you, Catherine. Thank you so much for the very stimulating talk, although the details are not so easy to digest. Okay. Before we continue with the question and answer session, we will have a short break. Pak Eddie, would you please?
Okay, yeah. So let me see. So we are going to present you some song from Indonesia. This is a folk song, Catherine. This folk songs. This song is actually a medley song from 4 folk songs, yeah, different folk songs, yeah. First one is Angin Mamiri from South Sulawesi, and then Ais from West Java, and then Buka Pintu from Ambon, and the last one will be Cik Cik Periak from West Kalimantan. And these songs performed by ITB student choir alumni, and Hilda and Rinovia will be in that singer as a singer of these songs. Okay, so enjoy the song, yeah. Okay. Hopefully you enjoy the song.
Oh, it's beautiful singing and beautiful clothes as well.
Okay. Bu Hilda, continue the session.
Yes, thank you, Pak Edi. I think there is a question from Bu Kiki in the chat. Bu Kiki, I invite you to ask Catherine directly.
Sorry, hi
Hello,
Catherine,
Kiki.
nice to meet
Hi,
you.
Kiki. Nice to
Yeah,
see you.
so I'm wondering because like you said in the third application that there is a possibility to like have the algorithm cannot find any random hypergraph, or there is there is a case that we cannot find any hypergraph with many techniques or algorithm.
Yeah, so I think the NP completeness result says that for some degree sequences, you can't even decide whether a hypergraph exists with that degree sequence or not, which is very surprising because in graphs, of course, we have the Erdős-Galay conditions that you can quickly check, and you have the Havel-Hakimi algorithm that will check the conditions and give you the graph. And yet in hypergraphs, sometimes you can't even tell. But for our, I guess for what our algorithm says is anytime you have an algorithm for generating the bipartite graphs, what does it tell you? That, yeah, if you can generate the corresponding bipartite graph, and if it's possible enough that you don't get those repeated neighborhoods, then you can also generate the hypergraph. And by generating one, you sort of prove that one exists. So it tells us that there will be some degrees for which we just won't be able to sample. But just like with the traveling salesman problem and the Hamilton cycle problem, there are fast algorithms that work almost all the time, even though we know that they're NP complete problems.
Okay, thank you. Thank you, Bu Hilda.
Yeah, terima kasih Bu Kiki. Okay, is there any more question?
Yeah, I see a question from Joseph in the
Oh,
chat.
yes.
Yes.
It's quite long. I will invite Joseph. Joseph was next student as well, Catherine.
Yes, I remember.
Oh, you know him. Okay.
I'm not sure if we've met, but I've seen Joseph's name.
Yeah. Joseph?
Hello, Catherine.
Hi, Joseph.
Hi, Joseph. Okay.
Yes. So my question would be about the, if instead of we let the random bipartite graph to be generated over and over, can we actually make some correction? So suppose we have a failed bipartite graph, and then probably we can just adjust it a bit so that it can directly go into the simple hypergraph instead of generated over and over. Is there any kind of technique?
Yes, that's a great question. So I think that it should be possible, and this goes back to some work that Jane Gow did with Nick Wormold, where they said in the configuration model, you generate one of these configurations, you look at it and see if it has any problems, if it has any loops or multiple edges. And if it has even one problem, you throw the whole thing away and you start again. And they said, this is wasteful. Instead, if it only has a small number of problems, you can do as you suggest and use some sort of switching operation to get rid of those problems. And somehow, if you do it nicely, you keep everything uniform until the end. So this probably will work for hypergraphs as well. In the Arman, Gow and Wormold paper where they do the bipartite graphs, I'm not actually, I don't think they looked at hypergraphs, but Nick and I and Nina Kamchev, when she was at Monash, and Mikhail Isaev, we were working on this, and we all met together once, and then the pandemic happened, and so it's been difficult to push it along. So we think that we should be able to do this, and in order to follow the approach that you suggest, we needed to look at sampling bipartite graphs, and we wanted to make that algorithm better. And then it ground to a halt. But the first part of your question, I see you also typed in, does it have to be uniform? And the answer is no, not really. You could, just as we can sample graphs with different degrees on the left, there's no real reason why all the edges should have to have size R. You could just generate a bipartite graph with different degrees down here on the left. But we decided to keep our life simple and just use uniform hypergraphs in that paper. But it should generalize.
Mm-hmm.
Thank you very much.
You're welcome.
Okay, thank you, Yosef. Now, maybe I would like to invite Professor Obata to give a comment. Professor Obata, are you still here? Oh, maybe
it's not connected anymore. So,
oh, I think he's already left. Yeah, I didn't see his name anymore.
Can I have one question?
Yes, please, Pak Edi.
Okay. So thanks. It was wonderful talk, Catherine. And you mentioned a lot of nice applications of your results. I just wonder, is it possible to apply your result to approximate the number of different Ramsey minimal graph for a given G and H? For example, like if you choose G as a matching, and then H is a complete graph, for example, or small graph, or other graph which is not dense, yeah. So we know that the set of these Ramsey minimal graph are finite, because in some pair tends to be not finite, yeah, you can be infinite. So for this set, for matching versus other graph, the set of this Ramsey minimal graph is finite. So is it possible to
yeah, I see what you're saying. One thing about the stuff that I do, and that some of what Nick does and Brendan does, because we're working with random graphs or hypergraphs, often they don't have much structure. You know, if you just choose a random graph with given degrees, it, for example, it doesn't have any automorphisms with high probability. It's really got no structure, whereas most graph theorists are working on beautiful graphs with lots of special properties and lots of structure. We're working on, you know, a lot of what I do, it's not really looking at the properties of the graphs, nice properties. You're just looking at a random graph and seeing what properties comes out of the randomness. So in order to be able to apply it to something like Ramsey minimal, I think you'd need to know quite a lot about what the Ramsey minimal graphs look like, which you probably do. I don't know a lot about that area myself, but you probably also need it to be sufficiently like random or pseudo-random in some aspect so that we could still apply the enumeration. And sometimes I think these special graphs have got too much structure, so they sort of fall out of what we can handle completely. But someone who might know more than that is Anita Libernau, who's at UNSW these days, and I really need to do some work with her because we haven't worked together yet. But as well as knowing about the enumeration stuff, she also knows about Ramsey and minimal Ramsey results. So she would be a good person to try to put those things together if possible.
What is her name?
Anita Libernau. So she's the one who had the sort of breakthrough result with Nick. And I think that's not her main interest. She's interested in you know, maker breaker type stuff on graphs, and also Ramsey questions, and a bit of what do you call it? Additive set, like combinatorial arithmetic combinatoric stuff these days as well. So she's got some very interesting research interests.
Okay, thank you very much.
Okay, thank you, Pak Edi. Is there any more question or comments for Catherine? Okay, I think once again we thank Professor Catherine Greenhill for sharing us her current research and development in random hypergraphs, which is very motivating. And now I think I will hand over the program back to Professor Baskoro. Pak Edi.
Okay, so thanks again to Professor Catherine Greenhill for wonderful and inspiring talk. And on behalf of the ITB, Faculty of Mathematics and Natural Sciences, we would like to present you some certificates and also some token of appreciations. So let me present you some certificate here.
Cool.
Okay. So this is the certificate of your talk, and just a moment. Let me. I couldn't.
Itu ya, yang green bukan?
Yeah. Just a moment. Let me see.
Itu, ya.
Okay.
Oh.
So,
Got too many tabs open.
too many. Let me.
It looks familiar.
This one, Pak Edi? This is the one?
No. Just a moment. Let me see.
Tutup tadi.
Oh.
Nah,
You are. Okay, so this is
Wow.
this is the token of our appreciation.
That's
So
amazing.
I will send you these two documents, yeah, by email.
Please.
So thanks again, Catherine, for a wonderful talk today.
Thank you very much for inviting me.
Okay, so see you next time, and hopefully next time you can come to Indonesia to visit us, yeah.
Yeah, that would be great.
Okay. So thanks again to everybody who be in this program today, and see you next year, because for this year we finish all this program, yeah, for Combinatorics to this series, and we continue next year. Okay, so thanks a lot again, Catherine. And
Thank you.
Bu Hilda, and also all the committee, yeah, Ibu Prita, Pak Joko, the head, the chairman of our research group, and also all the members of the research group, yeah, and also to everyone here. Thanks. Yeah. Okay. So bye-bye.
Bye-bye.
Okay.
See you next week,
Thank
Catherine.
you, Catherine.
Yes.
Yeah, thank
See you.
you. See you
Thanks,
next week.
Hilda.
Ibu
Thank
Kiki,
you.
terima
See you,
kasih juga
Hilda.
ya.
Bu
Sama-sama.
Kiki, terima kasih Bu Kiki.
Bu Kiki.
You are very welcome.
Profesor Obata,